Hello everybody, this is the first video for chapter 5 of the statistical learning class. So for previous chapters we mainly focused on the regression problem where the response we tried to predict was numerical or was quantitative, whereas here for this chapter we'll instead focus on classification problems where the response is qualitative. So we're gonna introduce a few methods for classification. The first one being K-nearest neighbors. Then we will discuss linear and quadratic discriminant methods and logistic regressions. So these are possible classification methods. There are plenty of others, but these are the ones we're going to focus on for this chapter. So this chapter presents parts of the chapters 2 and 4 from the ISL textbook and chapter 2 from the ESL textbook. So classifications problems, they're not only theoretical, there are many real-life problems which can be phrased or expressed as classification problems. So here I give a few examples, but of course there are a plethora of other problems that are classification problems in practice. So the first one we can think of is a person arrives at the emergency room with a set of symptoms which could be possibly attributed to one of three medical conditions. So what we'd like to know is what of the three conditions does the individual have? Okay, so does the individual has condition 1, condition 2, or condition 3? Okay, so we see that here this is a classification because 1, 2, 3, we can represent conditions by 1, 2, 3, but it's not ordered. Okay, it's distinct conditions, and these conditions can be understood as qualitative values. Second example of problem where the response is either 0 or 1 or true or false is the following. So an online banking system or service must be able to determine whether or not some transaction that was performed on some website is on the site of the company is fraudulent or not, based on many features of the transaction, such as the IP address, past transaction history of that person, etc. Okay, so their response should be either yes, it's fraud, or no, it isn't. So again, it's qualitative where we have two possible classes for the response. Finally, once more, the third one is an example with a 0-1 response, yes or no. So let's say you have some patients which have a DNA sequence. So the data for each patient is the DNA sequence. And some of these patients have a disease, some others don't have that disease. So let's say you're a biologist and you'd like to figure out which of the DNA mutations are causing a disease and which are not. Okay, so for example, you have many mutations. So based on the features of the mutations, you'd like to determine, is it causing a disease or is it not causing a disease? Or alternatively, you can not it can be either features of the disease, but or instead it could be features of the patient. Okay, so you look at the patient and you want to know, is that patient sick because of mutations or not? So for example, if you have a new patient, you can look at his DNA and then based on that look at his mutations and determine if he will be a sick patient or not. So there are many classification problems that can be expressed, that can be encountered in practice. So studying this topic from a statistical standpoint or machine learning standpoint is very important. So in a classification setting, what does our typical data look like? Well, once again, we have a set of data, x1, g1 until xn, gn, where small n is the number of observations in the data set. And the x's for each observation are the features or explanatory variables for that observation. whereas G here is the response. Whoops, sorry about that. So the response, we said we use the letter Y when it's numerical or quantitative, but when it's qualitative, instead we're going to use the letter G, and G stands for a group. Okay, so GI here is the response for the ith observation, which is qualitative. And here xi is the predictors, which can be a vector. So xi can have many components if you have many predictors in your problem. So the problem we consider here is to try to determine a classification rule. So what we mean by that, it's based on the set of explanatory variables x of an observation. You like to decide in which class the observation is likely to fall, or what's the likelihood of that observation to be of each respective class, G. Okay, so let's consider the following fictitious data set. So here what we have is we assume we have two explanatory variables, x1 being represented in the first axis and x2 being represented in the second axis. And then we have the response variable G, which has two possible classes, which are namely orange, represented by O, or blue, represented by B. Okay, so this data set was simulated with R based on some rule that I shall describe next. Okay, but here we see that this is a representation of the data. So for each point here, each point is an observation. We have the two predictors for each point, and the response is the color of the point, either orange or blue. So in practice, the problem we would face is, let's say we have new points that are provided in red here. So let's say we're provided the predictors for these new observations. So we know x1 and x2 for these new observations, so these new points here. What we would like to do is to try to determine if these points are more likely to be orange or more likely to be blue. Okay, so in practice, this point probably the vast majority of classification methods would set this guy as orange, this one as blue, and for this one it's not as clear, so it's going to depend probably on the methodology or the classifier we're going to select. So we're going to discuss such classifiers next, or at least throughout this chapter. Okay, so first what we're going to describe is how we simulated the previous data set. So what happened, this was simulated in R. I used 200 observations or 200 points, and for each point, first the class of that point was determined based on the following rules. So probability of 60% of being orange was used and 40% blue. Okay, so all the points were simulated independently. For each point, first we determined if it was an orange or blue based on that probability. And based on that, ultimately, the simulation provided 111 orange points and 89 blue points. Okay, so it's not exactly 120 like at the expected value. It slightly departs from the expected number of points, of blue points or orange points we would get. So now once the class of the points were determined, the predictors were then simulated based on the class. So for orange points, the predictors were simulated based on a bivariate normal distribution with mean vector 0, 0 and covariance matrix given by this. So you have a standard deviation of 1 across all dimensions, and the correlation between the two predictors is 0.5. Same here for the blue class. We also simulated the points, all points from the blue class, with a bivariate normal distribution with mean 2, 2 and some covariance matrix here. Okay, so we see that once again the points were positively correlated, and the standard deviation here is slightly smaller than 1, so it's square root of 8. Okay, so if we go back to the data set here, or maybe here, we see that the orange point, their kind of center of mass is 0, 0 here, as we said. It's the mean vector of orange point is 0, 0, whereas for blue, the mean point is 2, 2, so somewhere here. So we see that the points are simulated around 2, 2, or the blue points, whereas the orange points are simulated around 0, 0. And there's this kind of diagonal shape because the point for both classes, the predictors were positively correlated. So higher values of x1 are associated with higher values of x2. Okay. So about the classification problem, one thing that is relevant to notice is that many concepts that were discussed in the regression setting also apply to a classification setting. Okay, so the main idea is out of sample performance. What we want to have in a classification setting is ultimately good performance to predict new observations we've never seen in the training data. Okay, so if we have good good performance in our training data set, it does not mean our classifier is good, because what we want to do is to predict new ones. Okay, so the notion of underfitting and overfitting also applies here for classification. Okay, so same thing, the bias variance trade-off also apply. So if, for example, you have predictions which have a very high or a very high variance, and here the variance is different because the how we express variance here is a bit different because the response is not numerical. Okay, but so we cannot say the variance of the prediction per se, but let's say the variability of our prediction. Okay, so instead, if we have very variable predictions, which are highly sensitive to data points, then this still have the effect of potentially causing overfitting, which would mean good performance in sample and bad performance out of sample. Okay, so these concepts of mean variance, bias variance trade-off, they have to be a bit altered in the classification setting, but the overall idea remains the same, and ultimately what we want is good prediction out of sample. Okay, so as we said, we worked in a classification setting. So here, this representation of the link between the response and the predictors, which we had in the regression setting, doesn't make sense anymore. Okay, so in the regression setting, we often use the model that the response was a function of predictors plus some noise term. But here, because G is qualitative, adding a numerical noise term doesn't make sense at all. Okay, so this representation to link predictors and the response is not applicable for a classification setting. Okay, so instead, the link between the response and the predictors will be characterized by a function of this type, which is the conditional probability of being in the various respective classes once you set the predictors. Okay, so typically what we're interested in knowing is, for a given value of the predictors, what is the probability that the response is in a class G for all the possible G's. Okay, so if I give you predictors for an observation, I'd like to know, for example, there's 80% probability that you're going to be in the first class, a 10% probability in the second class, and 10% in the third class, or something like that. So this is the type of function which would characterize here the relationship between the response and the predictors in a classification setting. Okay, and what we attempt or hope to come up with is what we call a classification rule, which is a mapping from X to a forecast of its class G. Okay, so for some given predictors, you'd like to know, okay, the most likely class is class 2, for example, or alternatively, you can forecast directly the class, or instead forecast the probabilities of falling in each class if you'd like a whole distribution of the response. So what we'd like to have is the best possible classification rule, but to determine what we mean by best, we need to have some kind of metric to assess the performance of that rule. So the most simple and straightforward metric, here I wrote rule, but it should be metric here. So the most straightforward metric that can be used is the error rate. Okay, so what is the error rate? The error rate is the proportion of mistakes you make when you classify your observations based on that rule. Okay, so first we're gonna discuss the end sample error rate. So let's say we have our training data, and GI hat is the prediction you make for your ith observation, the response of your ith observation. Then the training error rate is defined as follows. It's defined as the sample average across all observations of an indicator which is worth 1 if you misclassify your observation. Okay, so if your estimated class is or predicted class is different from the true class, and 0 if you've correctly classified, so if your predicted class is the same than the true class. Okay, so this metric, the training error rate, is simply the proportion of classification mistakes you will make in your algorithm. Analogously, you could define the test error rate or validation error rate. So if you have a new data set, out of sample data set containing capital K observations where G0K is your kth response out of sample and X0K is your kth set of predictors for the out of sample data. So here the 0 represent out of sample. And these data are included in the initial training set. Then we can define the test or out of sample error rate as the average, once again, the average across all out of sample observations of an indicator telling which is worth 1 if you misclassify the out of sample observation based on your rule or 0 otherwise. So again, the error rate out of sample is simply the proportion of classification mistakes you will do out of sample. And of course, a good classifier is one that provides a small error rate in the test set. So you'd like in practice to minimize a classification error in the test set, which is a set of unseen observations during the training. So you want to know if your classification rule can be able to generalize to new observations well. Okay, so now we have to discuss some possible classifiers. The first one we will discuss is a theoretical one because in practice it cannot be applied, but we nevertheless have to discuss it because it will be a benchmark for many experiments we could make. Okay, so the base classifier is defined as the classifier which predicts the class of G, so of an observation, by its more likely value given its explanatory variable. Okay, so if you have an observation, then the base classifier predicts its class to be the most likely class given the predictor. So the class which maximizes the probability of being in that class for the predictors associated with these observations. Okay, so the conditional probability of being in that class given your predictors. It can be shown, so for a proof of that, please do the exercises, that the base classifier minimizes the expected test error rate. Okay, so if you want to minimize the error rate out of sample, the best thing you could do is to use the base classifier. So this is shown in the exercises. So it seems okay, we're done, we've solved our problem, but no, really we haven't, because in practice these conditional probabilities, they're unknown. Okay, so in practice, if you have the features or explanatory variables of an observation, you don't know the true probability of being in each class. So in practice, we cannot use the Bayes classifier, but so what we will need to do is to try to estimate these probabilities so as to try to mimic the Bayes classifier. Okay, so the true Bayes classifier is an unattainable gold standard, which would be an ideal case, but in practice, since these probabilities are unknown, the Bayes classifier cannot directly be obtained. So instead, we need to resort on estimates of such probabilities. So we would estimate the Bayes classifier. Okay, so if we go back to our previous example where we have exactly two classes, then the Bayes classifier would be of the following form. So for an observation, the observation would be classified as orange if the probability of being in the orange class given your predictors is greater or equal to 0.5. Okay, so if you have more than 50% chance of being orange for a given set of predictors, then you classify as orange. Conversely, you would classify as blue if you have less than 50% chance of being orange. So here, one quick note here, what we have here is the probability of a given class given the predictors. But in our simulated data, we did the opposite. So we first simulated the class, either blue or orange, and then based on this class, we had a distribution for the predictors. Okay, so in our simulation scheme, maybe I'll write this. The simulation scheme provided the distribution of predictors, which was multivariate normal, given the class. But what we need here to determine the Bayes classifier is the inverse distribution, the distribution of the class given X. So how to come up with this once you know this? Well, the answer is pretty simple. It's simply by applying the Bayes rule. So you saw in probability that the Bayes rule allows to get the probability of X given Y if you know the probability of Y given X. So I refer you back to your probability class notes if you don't remember what the Bayes rule is. But in our problem, these quantities can be determined by applying the Bayes rule. So we know this distribution here, and based on that, and we also know the unconditional distribution on G. So because we know this and this, we know the joint distribution of X and G, and thus we can compute the conditional distribution of G given X based on the Bayes rule. Okay, so our classifier, which has this form here, the Bayes classifier, which has this form here in our problem, will decompose the R2 plane into two regions. Okay, so why R2? Well, R2 is the set of the predictor space, in fact. So predictor 1 lives in R, predictor 2 lives in R. So the total possible values of the predictors fall in R2, the plane. So the classifier will split the plane into two regions. One region will be the values of the predictors for which the observation, okay, here there's the word observation missing, but the observation is classified as orange, and the values for which the observation is classified as blue. Okay, and here the frontier between these two regions will be called the Bayes decision boundary. Okay, so there's a line which separates the frontiers, the two regions, which is called the frontier, and on that frontier, the classifier is indifferent between classifying as orange or blue, which means that on this frontier, the probability of being orange is exactly 50%. So the Bayes decision frontier and the two regions and the R2 plane are illustrated here for our fictitious example. Okay, so here, based on the distributions we assume, so the 60%, 40% probability of being orange and blue, and the conditional Gaussian distribution of predictors based on the class. We could apply the Bayes rule to get the inverse probabilities. So these the probabilities of being either orange or blue depending on the various values of predictors. So based on that, we can calculate for each point x, so each vector in the plane x, the probability of being either orange or blue. And we now illustrate, so here in this region here at the bottom left, for all these points here, the probability of being orange was greater than 50%, whereas here in that region, the probability of being blue was more than 50%, and here the decision boundary, which are which is the frontier where the probability of being blue or orange is 50% is provided here. Okay, so this illustrates what we said earlier. So the decision rule splits the R2 plane into two regions, here and here, with the frontier. And in one of the regions, points would be classified as orange, and the other regions, points would be classified as blue. Okay, so we see that this rule misclassifies some points. So for example, the orange point here, if we had a new observation here, it would be classified as blue. So this clearly is a classification error, but of course, we don't expect the classifier to be 100% perfect. We still often want to leave some wiggle room for error, because otherwise that clearly would be overfitting. Okay, so now we will define the Bayes error rate. So the Bayes error rate is the expected error rate of the Bayes classifier. Okay, so the Bayes classifier is the one which minimizes the error rate, but it's often useful to know for that optimal classifier what is that smallest possible error rate. Okay, so for a given value of predictors x, the Bayes classifier always chooses the class for which the associated probability is the largest given that value x. Okay, so if you have 80% of being orange and 20% of being blue for a given value of x, then for that value of x, you'll classify as orange. Okay, so in that case, for a given value of x, so if you fix the predictors x, the probability of misclassification given these predictors is 1 minus the maximum across all classes of the probability of the class G given the predictors x. So why is that the case? Well, if we go back to our orange-blue example, let's say for a given value of x, the probability of being orange is 80% and blue 20%. So then in that case, the observation would be classified as orange, okay, which is where the 80% is the probability, the maximal probability associated to a given class. So here, when we would go over all classes, the maximal probability you would maximize between 20% and 80%, and that maximum would be 80%. Okay, so the most likely class has a 80% probability, so that maximum would be 80%. So the probability of error is 1 minus the probability of this maximal class, so it would be 20%. Conversely, if you had three classes, blue, orange, or green, and let's say you had, so let's say you had 60% probability of being, I'll use other colors, but red, and let's say you have 30% probability of being green, and you have 10% probability of being orange for the given value of x, then you would classify clearly as red, and here that maximum probability across all classes would be 60%, so you would classify as red, but when you classify as red, the probability of making an error is 1 minus 60%, which is the sum of probabilities of all other classes. Okay, so here if you have this example, the probability of making a mistake for this value of x is 40%, which is 1 minus the probability associated with the most likely class. Okay, so now to have the base error rate, so in the previous slide let's go back to the previous slide. This was for a fixed value of the predictor, but if we want to find the overall error rate, we must weight this whole quantity with respect to the likelihood or the likeliness of each possible value of the predictor. So the base error rate is the probability that for a random observation, your predicted class differs from the true class. So here we can use the double expectation theorem, where the unconditional probability is the unconditional expectation of the conditional probability. Okay, so here, so I don't know. So for those who aren't familiar with that result, probably you should have seen them in a probability class, but if you forgot it, so we have one result which says that for any random variables x and y that are integrable, then you should have expectation of x be the unconditional expectation of the conditional expectation of x given y. And here, if you have that x is some indicator variable which happens if event A occurs, then you have then this becomes the probability of A, and here this conditional expectation becomes a conditional probability. So this is here conditional probability of A given x. Okay, so here this is the rule we use. So we can express the unconditional probability of an event as the conditional expectation of that unconditional expectation of that conditional probability. Okay, so this unconditional probability of making an error can be expressed as the unconditional expectation of the conditional probability of making an error given x. So basically, the outside expectation would simply entail averaging that conditional probability inside with respect to all possible values of x and weight with the distribution of x. And here, as we had in the previous slide, when we fix the value of the predictors, the probability to make a mistake is 1 minus the probability of the most likely class given these predictors. The 1 can go out here, and here what we obtain is the following. So this is 1 minus the unconditional expectation of the probability associated with the most likely class. Okay, so this expectation outside would simply entail integrating that random variable with respect to the distribution of x dx, where x can be a vector here. So it's simply so the base error rate is 1 minus the weighted average based on the distribution of the predictors of the probability of making the right classification given that set of predictors. Okay, now one thing we have to notice is that the base error rate is something analogous to the irreducible error in regression. So since the base classifier is the optimal one in the sense that it minimizes the error rate, you cannot have a lower expected error rate than the base classifier, then the base error rate is a lower boundary to the expected error rate for any classifier. So it's kind of the amount of error you won't be able to remove regardless of what classifier you have. So it's the same thing for the regression. The irreducible error was kind of a lower bound where that portion of the error couldn't be removed regardless of what regression method you have. So here the same applies. The base error rate is the lowest possible error. So regardless of how good your classifier is, you won't have an error rate smaller than this quantity. So this is a portion of error which just cannot be removed. Okay, so as we mentioned, the base classifier cannot be used in practice because the distribution of the class, the true distribution of the class given the predictors, is unknown in practice. So if you have a data, there's nothing that tells you, well, here is the associated distribution of the class for each values of the predictor. So as we mentioned earlier, the base classifier is some form of unattainable gold standard against that is unattainable in practice, yes, but when we use simulated data or we develop new methods, it's always a good idea to use it as a benchmark to compare that with other methods. Okay, so when we do experiments and develop new methods, we can simulate fictitious data, and for this fictitious data, we know how we simulated it, so we would know the base classifier, so we can use that as a benchmark to see how the other methods compare to this gold standard. So in practice, we cannot use the base classifier because the true distribution of the class given the predictors is unknown. So what can be done is, in practice, is instead of using the true distribution, we're going to use a classifier which estimates these distributions, so the conditional probability of the class given the predictors, and then use these estimated probabilities to come up with a classification rule. So for the last part of the lecture, we will discuss one of such classifiers and leave other methods for future lectures and other videos. Okay, so one way to predict the class of an observation y0, whose predictors is x0. So if we have a new observation whose okay, so here I use y0. It should have been g0 because we use the group, but it doesn't matter. Here y0 represents the response, and x0 is the predictors for that new observation. Okay, so we can use a method called Knearest neighbours, which is analogous to what we had in the regression setting. Okay, so in the Knearest neighbours method, once we fix the integer k, the KNN classifier picks the k nearest neighbors of this new observation method. So the k nearest neighbors are the set of all data points in our dating data whose predictors x are closest to x0. And this set of points is denoted by n0. So n0 are the nearest neighbors to that point 0. So I could have added the superscript k here to show that the set of neighbors depends on the integer k we had. And then what happens is that the conditional probability of being in class G, okay, that the class G is J. So here G is a random variable, but J is a given fixed class. So the conditional probability that you end up in class J for the new observation is estimating as follows. It's the fraction or proportion of points in the nearest neighbors whose class is J. So basically this method estimates the probability of being in class J for your new observation as the average across all nearest neighbors of an indicator which is worth 1 if the observation falls in class J or 0 otherwise. Okay, so this quantity is basically the proportion of observations in class J for among the nearest neighbors. Okay, so in summary, what we do in this method is if we want to classify a new point, then we look within our training data for the k nearest neighbors, which are the k data points whose predictors are the most similar to the ones of the new observation. And let's say in this nearest neighbors, let's say there are 80% observations which are orange and 20% which are blue, then our estimated values will be, we estimate that for that new observation, the estimated probability is 80% probability of being orange and 20% being blue. Okay, so once again, the rationale behind this method is that observations with similar explanatory variables are expected to be likely to come from the same class. Okay, so if there are many training data points whose predictors are similar to x0, which are all orange, then you expect the new observation to be likely orange also. So this makes sense. Let's illustrate this concept with a very simple example. So this figure I've also picked or borrowed it from the ISL textbook. So thanks to the authors for authorizing to use these figures. So let's say we have a data set here and we have a new point x that we'd like to classify. Okay, so we still have the orange and blue framework where we have two possible classes, and we have a new observation where we'd like to know if this is classified as orange or blue. So in the example provided below, the k nearest neighbors method is used with k is equal to 3. So we use the 3 nearest neighbors method. So for this new data point, how the approach works is they try to find the 3 observations whose predictors are the closest to that new point x, and these 3 observations are clearly this one is the closest, this one is the second closest, and this one is the third closest. So these 3 points, this orange point, blue point, and blue point, are the 3 nearest neighbors. And for this new data point, based on this methodology, the estimated probability of being orange is 1/3, and the estimated probability of being blue is 2/3, because you have 60.6% probability of being, well, the proportion of blue observations within nearest neighbors is 2/3, and proportion of orange observations within nearest neighbors is 1/3. Okay, so this simple example illustrates how the k nearest neighbors method works in practice. So we can use this k nearest neighbors method for a classification on the original data set I've simulated and shown at the early stages of this chapter. So the KNN classifier was applied, and 2 distinct values of capital K were considered. So we considered a 1 nearest neighbor method and a 10 nearest neighbor methods. And we will compare the outcomes, classification outcomes, to the base classifier. Okay, so once here on the left side, it's the 10 nearest neighbors method. On the right side is the 1 nearest neighbors method. And once again, the figure shows all the points that were simulated initially. So the circles, orange and blue circles, are the data points. And once again, we have this frontier in red, which is the base classifier or base decision frontier. So here the red curve would be the best possible classifier in terms of error rate minimization. Okay, but now what happens if we use the k is equal to 10 nearest neighbors method? So here all the dots that were plotted, all the dots represent the class which is predicted for each values of the predictors. Okay, so here these data points would be classified as orange, 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 until blue, 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 blue. And same thing if you look at the second line, orange, 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 blue, 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 blue. So we see that the classifier K-nearest neighbors classifier differs from the original, the optimal base classifier, because if you're in this area, for example, the optimal classifier or base classifier would classify as blue because you're on the blue side of the optimal decision frontier, but the K-nearest neighbors method would classify as orange. Okay, so the classifier kinds of makes sense. So we see that overall there's more on that region, more points would be classified as blue, more points would be classified as orange here. So overall, these two methods provide somewhat decent results. But now let's look at the impact of K. Okay, so here, when K is large, you have to average many neighbors to determine or forecast the class of a new observation. And because you have to average 10 neighbors, some neighbors might be very far away from your current new observation. So because of that, you'll have to average somewhat irrelevant observations. And for that reason, so if you try to forecast a point here, we see that the 10 nearest neighbors here might be very far away. So 10 nearest neighbors might be here and here. So this is why in regions where the data is sparse, the classifier performs very poorly because it needs to use data points that are very far away. Okay, so because of that, when we have a very large K, the model is unable to capture the exact pattern here. So it's not flexible enough because it has to use points that are very far away. So we see that the method is biased because of that. It has to use many irrelevant points, but this has the effect of stabilizing the prediction. Okay, so why does it stabilize the prediction? Well, we'll compare to K is equal to 1 and understand this. So conversely, we see that for K is equal to 1, we have a bit less bias because the pattern is somewhat better captured. Okay, so there's somewhat a closer resemblance between the like optimal curve here and the regions classified as blue and orange. But for K is equal to 1, we see we have some overfitting. So if you're in this region here, we see that for these points here, the K-nearest neighbors would classify as orange because the nearest neighbor is orange. But in practice, this is not reasonable. Okay, so if you're in this region, most likely you should classify as blue because there are many more blue points in this area. So clearly, having classifying as orange here is some overfitting, which is undesirable, and this because K is too small. So we can see that when K is too small, the prediction would be very impacted by idiosyncratic data points. Okay, so because this idiosyncratic data point, orange point, is here, this impacts predictions here, and this leads to a lot of variability of predictions compared to K is equal to 10, where you wouldn't have a blue classification here because when you average across 10 neighbors, in this case, clearly there are more neighbors that are blue. So we see that when K is small, the predictions are very variables and very sensitive to outliers or single data points. Whereas conversely, when K is large, predictions are less volatile, but because you have to average very irrelevant points, this leads to biased predictions. So this is not good. Okay, so we can see that similarly as for the regression setting, then there's still that like variability bias trade-off when we select the proper value of K. So K too small, predictions are too variable. K too large, the model is too biased. So in practice, and K too small, too variable leads to overfitting. Okay, so in practice, how do we select the optimal K? Well, this would often be done through out of sample performance assessment. Okay, so what we can do is look at the various values of K, estimate or make make predictions based on our training data, and then look up on new test data how our original predictor performs. And if you have a low error rate out of sample in, um, let's say, a test set, then you know you've performed well. Okay, so in practice, the lowest training error would be obtained when k is very small. So if k is equal to 1, you're correctly going to classify all observations, but in the training set, but out of sample, because you have overfitting, you will perform poorly. Okay, so looking at out of sample predictive performance is what can help you determine suitable value of the nearest neighbors. Okay, now we've illustrated the k-nearest neighbors in a two-dimensional setting, so we have only two predictors. But what happens if we have the predictor space has a very large dimension? Okay, so if we work with a very high-dimensional classification problems where you have many predictors, then the k-nearest neighbors method would suffer the same setbacks that were discussed in a regression setting. Okay, so we won't repeat the full explanations once more, so please refer back to chapter 2 if you want to have a more in-depth discussion about this. But the idea here is that if we wanted to cover 100% times x of the total feature space volume, we need to cover for each individual predictor a range denoted by x to the power 1 over p for each features. Okay, so let's you can go back to here. I wrote chapter 2. I'm not sure if it's chapter 2 or 3 exactly. Probably it's chapter 3. So sorry, I said chapter 2, but chapter 3 instead. So the idea here is that in a very high dimensional setting, because most of the predictor space is unoccupied, okay, by observations, when you have to consider neighbors, the neighbors can be typically very far away and might be irrelevant for prediction. Okay, so if you work in high dimensional settings, for some problems, k-nearest neighbors might not work very well, so we need to identify other methods that could work well. Okay, so we will discuss the other methods starting in the next lecture. All right, so thanks for listening, and I'll see you for the next video.